Hello, this is Brian Washburn, and I'd like to continue talking about solving ordinary differential equations numerically using the ODE solver or Runge-Kutta type solvers using Python. I'd like to focus on two specific problems that we've already talked about in class. In class, we've looked at vertical or one-dimensional motion with either a linear air resistance or a quadratic air resistance. And what I want to do is I want to solve for one-dimensional motion for either case. And the nice thing, I also want to solve this using Runge-Kutta solver. Now, there are analytic solutions that we talked about. And so let me just talk about the two problems. The first problem I want to discuss is vertical motion with linear air resistance. So what I have is I have a coordinate system. I have some mass initially at times t equals 0 set to origin. And then what I'm going to do is I'm going to give it at times t equals 0 some initial velocity. That might point up, might go like that initially, or I can make it point down, whatever I want. Okay. Now, what I am going to do is I'm going to choose my coordinate system such that the y-axis points downward, and this is the way your book did it, which is somewhat convenient, but we're going to stick with your book notation. Now, there is a solution, and we derived this in class by setting up the equations of motion and integrating that. And we shown that the solution given initial, so basically what I'm going to say is that my initial velocity is going to be equal to up or down the y naught and the y hat direction. So if I throw it up, then I'm going to have the minus sign. Okay. If I throw it down, then I have the plus sign because the y-axis points downward. Okay. And this system here was actually derived for, yes, this is what we derived in class. Okay. And then we get exponential solutions. Okay. Now, I also want to solve this the equations of motion for quadratic air resistance. Again, I have the same one-dimensional motion again. My y-axis is going to point down. And I want to look at specific cases where, again, either I want to throw it up initially or throw it down initially. Okay. And then what I'm going to do is, again, my y naught initial is going to be, well, if I throw it up, I'm going to have minus sign. If I'm going to throw it, if I throw it down, throw it up a minus sign, throw it down positive sign, v naught in the y hat direction. So I want to be able to solve for both cases. There's an analytic solution that we derived by directly integrating the equation of motion, and we showed it was a hyperbolic tangent. All right. So I'm going to look at two Python codes, and I'm going to go over this. The first code I'm going to solve is what's going to be called physics linear air resistance vertical RK. That means in Runge-Kutta. There's another version on Canvas which just writes the exponential solutions. Okay. So I want to show, I'm going to talk about how this code works, and I'm going to show it solving for two cases, or actually three cases. One is I drop it, meaning it has zero initial speed. One I throw it up, and one I throw it down. Okay. All right. So let's kind of look at the code. Again, this is using the ODE class in Python to solve. Okay. So specifically, I'm going to load in my numeric packages in NumPy as an NP. I'm going to bring in this ODE class, which allows me to solve the differential equation. I include a new package called Interpolate, which I'll explain in a little bit how I'm going to use that. I'm going to use that to analyze the solutions. Matplotlib to plot things. Okay. And so what I'm going to do is first I start a timer. Time is a library for timing features. I'm going to start a clock that's going to measure CPU time. All right. So what am I going to drop here? I'm actually going to take an oil drop, and I'm going to throw it straight up or straight down or zero speed. It's an oil drop. Okay. So then what I'm going to do is define some constants. The gravitational constant, the diameter of the oil drop. This comes from your book, so I'm using numbers from your book. This is the beta coefficient from your book, the coefficient of linear air resistance. This is the density of oil. Okay. And then I can get the mass. So I assume that the oil drop is a sphere. And the volume of the sphere is 4/3 pi r cubed. I know the diameter, so that's where I get the 6 from, so that gives me the mass. Then I determine the constant beta. Beta is basically, B. B is beta times the diameter. And then the terminal velocity. Remember we showed that at terminal velocity that the resistive force is equal to mg, and this gives me the terminal velocity. Now that's going to be important. So I have an analytic expression for a terminal velocity. I'm going to compare it. In class we defined something called tau. Tau is basically a time constant, the time it takes to reach 1 over e of the terminal velocity. That's what tau is, and we derive that. Okay, so let's talk about the code itself. I'm going to print out to screen here the terminal velocity in tau. I'm going to define the differential equation. Okay. Now notice that the differential equation is a first order, not coupled differential equations. It's one-dimensional motion, so the differential equation is quite simple. All right. And before I do that, let's go back and actually look at the differential equation I have. So I'm going to go back to my lecture notes I have here. So that's my solution. Let's take a look at my differential equation. Again, what we did was, using F equals ma, we showed that mass times acceleration, and we wrote this differential equation in terms of just v and v term. V term is a constant. So if you look at this differential equation, it's first order, uncoupled ordinary differential equation. Okay. So when I write it in for my Runge-Kutta solver, I'm going to divide by m on both sides. I'm going to say that v dot is going to be equal to minus b over m divided by times this constant v minus v term. That's my differential equation. Going back to here, this is my form. Again, I have b over m times, now again, y0 is going to be my v in the y direction minus v terms. So that's a very simple form of my differential equation. Okay. I have another definition here called solve equation. I'll explain that a little bit later, but let's solve the differential equation first. I'm going to pick 5,000 points. Okay, it's a good number. And then I pick a time range from 0 to 5 tau. I expect, remember tau is a time constant, so definitely I should reach the terminal velocity within so many times, 5 or 6 times that time constant. So I just pick 5 here. Then what I do is I define, so here I'm defining the time range like we did before. I had to create an array of time values. So my maximum number is 5 times tau. dt is going to be the time range divided by the number of points. Okay. And so that's going to be 5 tau divided by 5,000. If I just type that in, I get, now remember, tau is a very small number. Actually, maybe didn't see it. Tau is actually microseconds. Okay, so this thing, so for oil drops, and your book talks about this, oil drops are going to hit terminal velocity incredibly fast. So the time it takes to get to this is going to be 6 times this number here. So about 36 microseconds. It's going to hit terminal velocity really quick. And this is part of the reason why oil drops were used in the milk and oil experiment, because they hit terminal velocity really quickly. Okay, so seconds aren't going to be a good time scale. Really, microseconds is a better. Okay, 10 to the minus 6 seconds. All right, but if I take, what is 5 tau? 5 tau is going to be equal to, okay, that's my 30 microseconds. All right, so now what I'm going to do is I set my time range. dt is going to be again 6 nanoseconds. So I have good resolution on time. Okay. And then I create my array of time values that go from 0 to times 5 times tau. Okay, so I set up my time array. Here I'm going to give it an initial condition. Okay. In this case, notice that it's minus 5. That means I'm going to give it a velocity of 5 times 10 to the minus 5 meters per second upward. Okay, and remember my coordinate system points down. All right. So now what I'm going to do is I'm going to solve it. I set y0 is going to be an array of solutions. I define it by giving an empty set. And then vy0 is my initial condition. I just append that as the first element. Now I'm ready to solve it using my Runge-Kutta solver. I define R as something of class ODE. Okay. I tell it how to integrate it, what kind of integrator I'm going to use. I'm going to set the initial conditions, the initial speed at times t equals 0. That's what I'm doing there. Then in a loop, I'm going to solve So I take each element in t except for the very first one. Okay, just remember t0 is the very first element, t equals 0. t1 should be just dt 6. Okay, so I'm going to start from the first element to the last element. Okay, so if I type in this, it's going to give me all the elements in t except for the very first one. Okay, and you may say, well, what's the very last one? There's actually a cool index. We can do that, and it actually gives me the very last element of the array. Okay, so tt is an element in t starting from the second element to the last element. I'm going to solve the differential equation at time tt. I'm going to take the solution and append it to my solution array and give me a warning sign if I'm not solution, if it didn't solve it. Okay. Then I'm going to take my solutions and create it as a numpy array. So now I have these guys here, all my velocities as a function of time. I want to get position as a function of time. In order to solve that, I'm just going to integrate this using cumulative sum. All right, so let's run the code. And again, what we're going to do is we're going to run the code for -5 up. Okay, I run the code. And you can see, okay, take a look here. So again, my times are really quick. So I plotted them in microseconds. And notice that at times t equals 0, I'm at -5 times 10 to the -5. Okay, so I'm basically throwing it up. And what this thing does is it starts slowing down, gets to 0, and then speeds up in the opposite direction, and then hits the terminal speed. And notice after so much time that it's going to hit that terminal speed. Okay, and it gets to it pretty close at the 30. Okay, again, I just arbitrarily chose my time to be 5, even given my initial condition. Okay, now let's take a look at y as a function of time. That's what I'm plotting here. I start at the origin. It goes, remember, a negative number is actually going up. So it goes up, it comes back down. At this time here, it comes back to where it started, and then it keeps on going down, 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 down forever. All right, so that's what's going on there. So that makes sense. It goes up, and comes down. Okay. Now we can solve this for a couple of other cases. We can solve this for 0. I'm just going to type 0 times that. If we solve that for 0, oops, why did it do that? Hold on. So let me resume. The reason why it gave me an error was because I was actually looking for some roots, which I will do in a minute. But let's set this to 0. Let's run it. If I set it equal to 0, then what happens is I start off at the origin. I start at 0 speed, and then I exponentially get there, and I almost get to there at, roughly so many time constants. Okay, and then the thing just starts from the origin and it falls and goes positive height. Well, that's falling further and further down. All right. Now let's do the last case where I just throw it down. Okay, if I just do that, then what happens is, again, it starts at speed downward, kind of goes up and up and up until it hits the terminal velocity, and the height just continuously goes down, down, down. Okay. Okay, so that's what's going on there. Let's try to answer some physics questions here by doing this. So let me do this. Let me throw it up. Okay. And if we take a look at our solution, notice, and then let me go here. I'm going to plot this guy, and what I'm going to do here is I'm going to plot y as a function of time, and I'm going to say y lim is equal to so I'm going to do minus 0.2, and then I'm going to do, say, 0.2. And then I need the alias. Okay, so I just do that. Okay, and let's just run this again. And I made a mistake. Why did I do that? Okay, so here I made a mistake. Let me run it again. The mistake I made was I can't forget these are really small increments. So I need 2 to the 0.2 times 10 to the minus 9. Okay, so now if you notice, this thing kind of goes down, it comes up. Say I want to solve for that time. What time? How long does it take to go up and then back down? Okay, So you can see with just from looking at the graph, and then what I can do is, okay, let's actually zoom in a little bit more, and then what I can do is say, all right, from 0, I gotta be careful about time, 0 to say, I don't know, 10 microseconds. Let's see if I did that correctly. No, I did not. Let me do it again. Okay, I fixed it because I fooled myself again. I'm plotting already in microseconds. Okay, so take a look here. I go up and I go down. And then notice that I cross the x-axis, or sorry, I come at y equals 0 roughly about 8, 8.5, maybe 9. Well, it's less than 9. So that point right there. Okay. So say what I want to do is I actually want to solve for that time. Okay. How do I solve that? Well, in some respects, mathematically, what do I have to do? Well, mathematically, let's think about it. All right, let's go back to here. And, what I really want to do is, okay, so I have a function, in general, I have some y of t. That's what I have. And really what I want to do is I want to solve for the equation y of t at little t equal to big T, where that's equal to 0. Okay, now notice my function did something like this, and here, and it came up here, and went like that. And so what I expect to see is, oh, there's going to be two answers. There's going to be this guy, this guy. Okay. Now, if I had an analytic expression, or say it was a parabola, like we did for projectile motion, you could just use the quadratic formula. Again, what I'm plotting is y, and I'm plotting time here. Okay, you could use a quadratic formula. First of all, I don't have a formula. And second, I just have a list of numbers, and so I have to use a computer to do that. So how am I going to do that? Well, what I'm going to do is this, okay? I'm going to basically take my code, okay? Remember, again, what I have is I have a solution. I have a list of y values, and I have a list of time values, okay, as arrays. And what I'm going to do is I'm going to take this section here, some data, some section like that. I'm going to create a function in Python that's going to interpolate this function. I'm going to call it f. Okay, that's my interpolation function. And then I'm going to look for a value of f where it's equal to 0. That's called a root finding function. All right, that's how I'm going to do it. All right, and so exactly how I'm going to do it, well, that's what this little procedure up here does. Let me explain this little procedure. All right, it's a little bit complicated. So what I'm going to do is I'm going to use something called interpolate in Python. Okay, and I call the function called solve equation. Basically, it says given a function f of t, solve for the value big T where f of t equals a. Now in my case, a is going to be equal to 0. Okay. And so what I'm going to do is I'm basically going to create arrays of. So what I'm going to do is I'm not going to use all the data points. I'm going to use a small set of data points that's near the 0. Okay, so I'm going to look at values of my function near the place where it crosses 0. So that's what this stuff does. This line here calculates the interpolation function, and this thing here basically calculates where the root is, and it gives me a time value for the t for the root. Okay, so how do I actually use it in the code here? I had it here, so I had it commented. So let me uncomment. Oops, why did I do that? Because it's stupid. There we go. So what I'm going to do is let me just run it and then explain how I do it. Okay. So then you can see here that, okay, this guy goes up and it comes back down. It's about 8. And notice that I actually calculated 8.365 microseconds. All right. How do I use this function? So I give it the t values. I give it y. I say, okay, solve the equation y equals value 0. Okay. And then look from the range from 0 to 10 to the minus 6 seconds. So it's going to look from 0 to here. Now, it doesn't give me the 0 point. That's what I could do is I could say, if I didn't want this point, I could even say, 1 e minus 6 will give me the same thing. That's probably a better thing to do. Okay. And I get still 8 seconds. So it's basically looking from here to here where it crosses 0. And then it gives me that value. TS is the answer. And then what I say in the code is the time for the drop or the oil drop to go up and down is Y is 8.365 seconds. Okay. All right. You can also use this code to calculate. All right. Let's see. How long does it take for the speed to reach terminal velocity, or 95% of the terminal velocity? Okay. And you can see, just looking at it here, I'll notice that, all right, this guy here comes up here, I don't know, maybe 25 seconds or something like that. So then I can do the same. I can use the same code. Solve equation. T, instead of y, I put Vy. And then the term I want it to get to is 95% of this. And then I have to give it some range to look. So I'm going to look from 10 microseconds to 30 microseconds. That's 10 to 30. That's this range here. And if I run it here, it should spit it out. Again, looking at it here, it says here, okay, the time for it to go up and down is 8. The time to hit 95% is 22.2 microseconds. And if we look at the graph, 22 point, it's hard to say exactly what it is, but that's, I can believe that number. That's about 95%. Okay. If I want to know 98%, I just type in 98 here, run it again, and it says here 27. Okay, 27 seconds, that's about here. Okay. So you can use these, the solve equation function is going to be very useful for actually analyzing data. All right. Okay, so let's move on to the next problem. Again, what I want to do is I want to look at air resistance, but the same problem with a quadratic air resistance. All right. So that is going to be the program Phys 522 quadratic air resistance. All right. And let's take a look at this code again. Now, this case, it's not going to be an oil drop. It's going to be a baseball. And again, I want to have the ability to throw it up or down. Okay. Depending on whatever my initial condition is. Okay. So I integrate the same packages again I did before. I'm going to use the interpolate function again in order to find times. Now the physical parameters, so in some respect you can use the same exact code. It's just now you have to, what's going to be different, we use gamma instead of beta. Okay. And the terminal velocity is going to be a different expression. Okay. That we had for quadratic air resistance. Okay. So what I did was I switched over to our lecture notes, and this is my situation I have. Again, let me just show you the equation of motion before I show the numeric stuff. I have y pointing down. My terminal velocity is by looking at the equilibrium condition. Okay, and then what I did was I rewrote the equation of motion in terms of the terminal velocity, and I got this guy here. Now, as we talked about in class, this equation here is a little suspect, because if I put a minus v here, I'll always get a minus sign here. If I put positive v here, I also get a minus sign. So that this right-hand side of this equation doesn't change based on my initial condition. That's a problem. That means that independent of my initial conditions, my frictional force always opposes gravity, and that's not physical. So what I have to do is, again, there's a problem with this expression here. And this is what your book has, but the book was assuming you just threw it down or you dropped it. That's not correct. So in order to correctly, because remember that if you multiply, remember this is the net, this side of the equation is the net force divided by mass. Well, this side is gravity, this is air resistance. They're always oppose each other, independent of how you throw it. If you throw it up, then gravity, the force of gravity and the force of air resistance will point in the same direction. That's not consistent with this equation. So in order to get that, okay, I have to put something called the sine function, or basically this thing here gives me a sine of whatever that v is. Okay, so if I throw it down, all right, then remember my v at time equals 0 is positive. Remember the x-axis or the y-axis points down, so then I'm going to get a minus sign here. If I throw it up, then I'm going to get a minus 1. That makes this a plus, and then that's the case. Remember, if I throw it up, the force of gravity and the force of air resistance will point in the same direction. If I throw it down, they'll point in the opposite direction. So I have to account for this in my code. If I don't do it, I'm going to get a mistake. All right. So going back, how do I do this? Okay, this is the code we had here. And NumPy has a nice feature called sine. Okay, so remember y is v. So I define this is a y0 is a one element array, and y0 is going to be the speed. Okay, so this is the same differential equation I have here. Okay, so that gives me the sine. All right. I'm going to solve this in exactly the same way we did before, so I'm not going to go through that code. So let me look at some cases. Okay, so what I'm going to do is I'm going to set the initial speed to 0. So that means I just drop it. And let me plot. Okay, now let's take a look what's happening. Is that times t equals 0, I have 0, and then again, it's not exponential, it's this hyperbolic tangent business. I guess that's an exponential. But anyhow, it does a hyperbolic tangently, moves up to the terminal speed. Okay. And then in order to get the height as a function of time, what I do is I just integrate using this term here, using cumulative sum. All right, that's cool. Okay, so that's what I expect to happen. Now what I want to do is let's throw it down. Okay, let's throw it down. And then let's go, I don't know, plus 10. So remember, plus 10, that is throwing it down. Okay. And let's take a look at that. So it starts at 10 and then reaches the terminal speed here. All right. And then in 0 goes through here. Now, you want to see something cool? Yeah, this is really cool. I want you to explain this. I'm going to set this to v term. All right. Let's look at the solution. Look at that. Yeah, throw it down. And then it doesn't change its speed at all. Why is that? Does that make any sense? Well, yeah, it does. I want you to think about that. Okay, why, if I throw it down at the terminal velocity, is the velocity as a constant of time? All right. Okay, now I didn't do a very good job of my number of points. I should have made that. Let's make that 1,000. It doesn't matter. Okay. Now let's throw it up. Okay, we're going to throw it up. Where are we? Already I lost it. Oh yeah, here we go. We're gonna throw it up and we'll do minus 10. Remember the x-axis, the y-axis points down. Throw it up. What do I get? Okay, so here notice that it goes up and it comes down, and here it starts at minus 10, hits 0, and then keeps on going and goes to that. All right, that's what's going on. Now just for giggles, let's make this minus v term. And see, you can see here it goes down, it goes up, goes down, and eventually hits v term. All right. So that's what's going on. Now let's try to answer some more questions again. Let's ask, all right, how much time does it take to reach from 0 to the maximum height? That's a new question. Remember what we did before was we calculate how much time it takes to go from 0 to go up and go down. How much time does it take to reach the maximum height? How the heck are we going to do that? Well, there's a cool thing we can do. If I say MP min of y, I get a number, minus 42. Does that look like minus 42? Yeah, that looks like minus 42. Okay, so what I'm going to do is I'm going to use the existing code I have, all right, and I'm going to use this code here. Oops. Okay, so what I'm going to do is I'm going to highlight that and uncomment that, and I'm going to uncomment that. So now notice what I have here is I don't want to do 0. I want to find the time it reaches the minimum. So I can say instead of 0, np min of y. Now here I have to give it guesses, so it's somewhere between 2 and 4. 2.0 and 4, and then and just the time for the ball to reach its max height is blah. All right, let's see if this works. and 2.7 seconds. Yeah, okay. Sure, I can believe that. Okay, so the time it takes to reach is 2.7 seconds. All right, so that's what this code does. Now, a couple things about this. See that this thing here, TS, what is TS? TS is the value of the time. What the heck is IDX, man? This function gives out two things. IDX is the index that's closest. So if I say T of IDX, that is an integer, they're not going to be exactly the same because TS is a number that may not necessarily be in my array. But if I say Y of Y IDX, okay, Y IDX that's minus 42. That's that number there. And, oh, here's something. Yeah, Vy of IDX. That's a small number. Okay. Should be very close to 0. Remember, the thing goes up. At the top, it stops and then turns around. Okay, and the reason why not exactly 0 because my time TS doesn't really occur at one of my times of my array. It's close, but not exactly the same thing. Okay. So what I've shown you here is how to solve equations numerically. But then the really important thing to do is be able to take your numerical solutions and answer simple physical questions about it. Simple physical questions might, okay, how long does it take for it to go up and down? How long does it take for it to go to its maximum height? How long does it take for the velocity to hit 95% of its terminal velocity? Okay, that's the important thing you can do. And the nice thing with the numerical solutions, you can do it very easily just by modifying the existing code. All right, that's it. Take care. We'll see you later. Bye-bye.